Hello everyone, my name is Dr. Muhammad Furqan Madni, and in this video, I'm talking about orthogonal blinding or artificial noise-based physical layer security techniques. Now, starting from some basics, there are a lot of interesting applications of wireless communication in almost all chapters of our life, from autonomous car to smart cities, smart homes. Almost in every chapter of life, we have interesting application. However, due to the broadcast nature of wireless communication is vulnerable to several security threats. For example, if you see this figure at the right of this slide, we have an eavesdropper attack where an attacker will try to listen the features or the content of the communication. And the solution to eavesdropping, corresponding to eavesdropping, is confidentiality related algorithms. Then the passive attacker will not interrupt to the basic communication, just listen. On the other hand, active eavesdropper can jam your communication, can launch impersonation or spoofing attack, and possible solutions to these attacks include authenticity, integrity, and availability related stuff. Now, starting from the basic, in order to tackle the different security threats in wireless communication, conventionally we are using cryptography based algorithm in which we require to share secret key between the communicating nodes. It is efficient, it is providing us security, but the biggest problem with such techniques, the biggest problem corresponding to these techniques include secret key management. As you know, when we are going towards future wireless network, where we have a heterogeneous wireless network structure or configuration, the key sharing and key management is very challenging in such cases. Moreover, there are some wireless applications such as autonomous car or remote surgery. These applications are latency sensitive. Cryptography based techniques cause extra delay, which these applications cannot afford. So, in order to tackle these issues, physical layer security techniques are complementing the conventional cryptography based algorithm. In cryptography based techniques, secret key can be extracted from the wireless channel between two communicating nodes, so it can solve the problem related to key sharing and key management. Moreover, physical layer security techniques can exploit other features of channel interference, fading features of channel for providing security at physical layer. Actually, in physical layer security technique, in cryptography based techniques, you are applying key at the application level on the data to provide security. On the other hand, in physical layer security, we degrade the listening capability of the attacker. This is the basic theory of physical layer security, in which we are not applying something at the data level. We are degrading the listening capability of an attacker. We can use an interference, we can use adaptation based techniques such as beamforming to achieve this goal. Now, if we summarize popular physical layer security techniques, we have key generation based techniques, in which the basic idea of physical layer key generation or channel based key generation is that it is based on two basic assumptions. The first one is reciprocity, which ensure that the channel observation at the legitimate node, here Alice and Bob, the channel observation observed by this node at the end of this link is similar or approximately similar. And due to the spatial decorrelation concept, in which the observation of channel at different node, which is half wavelength apart in rich scattering, will be different. Under this assumption, we can generate secret key between Alice and Bob can generate secret key based on their similar channel observation, and an attacker will try to extract key from her channel will be different from their channel. Other physical layer security techniques include channel-based adaptation techniques, in which the transmitter, legitimate transmitter, adapt the transmission based on the requirement of legitimate node to provide security. For example, beamforming based techniques. Finally, recently reconfigurable intelligence surface are also providing adaptation based security technique, in which we design RIS in such a way that the signal will constructively add it to the legitimate node, while at the attacker we will make sure that the signal will add destructively. Now, these are the popular security techniques. Coming to the orthogonal blinding or artificial noise-based security techniques, the basic idea here is that we are using interference or noise signal to enable secure communication. The starting of this concept is actually started by Niki and Goel in 2005. These are the initial works by these authors, in which they show that how we can use artificial noise for secret key for providing secure communication. From this basic concept, this diagram, I tried to show what's going on. Actually, we have a legitimate consider system model where we have an Alice that have multi-antenna. Assume we have two antenna at Alice, and there is a legitimate receiver Bob and an illegitimate receiver Eve that is trying to eavesdrop our communication. Now, here the idea is that we want to add a noise signal at legitimate node in such a way that when it passes through legitimate channel, the legitimate receiver will not receive anything. I mean, will not receive any noise signal. We will design the noise signal in such a way that when it passes through channel at the legitimate node, it is transparent. It will not see any noise signal or any interference. On the other hand, due to our design of noise signal based on the channel of legitimate node, and the attacker will receive the noise signal, because we add the noise in such a way that it will hurt the illegitimate node while without hurting legitimate node. As you see from this figure or another visualization of what's going on, is that we have a legitimate transmitter that is transmitting at the legitimate node. The legitimate signal or signal of interest is easily detectable. On the other hand, attacker will suffer from the interference. So if we say how can we define, is in orthogonal blinding, secure communication is achieved by adding an interference or jamming signal to the transmission to degrade the attacker performance, while least possible or no harmful effect on the reception of legitimate receiver. Now, how we are achieving it? We are achieving it by exploiting the null space of legitimate channel. So what is the null space of legitimate channel? Here are some more definition of orthogonal blinding or artificial noise-based techniques. You can go over these techniques. For example, the interference signal degrade the attacker performance while ensuring least possible or no harmful effect, as I explained earlier. Or in general, in this method, we are trying to conceal the user signal with the help of noise. I want to mention this. One of the assumption is the number of antennas at Alice should be greater than number of antennas as Bob to enable null space of channel. And initially, it was also assumed that or this assumption need to be fulfilled that number of antennas at the eavesdropper should be less than legitimate transmitter. But recent work shows that it is, for example, this work shows that even if the attacker have more antennas than legitimate transmitter, we can still achieve security. Now, what are the merits and demerits of artificial noise-based security techniques? First of all, you can achieve a very strong security technique, very strong security at any distance from the transmitter in fading or non-fading environment by artificial noise-based techniques. Another interesting benefit is that because you are designing the artificial noise based on the transmitter, at transmitter based on legitimate channel, so you don't need to do any extra processing at the receiver. Transmitter will add a noise signal when it passes through the channel of legitimate receiver. Legitimate receiver will not receive any noise signal or very least effect. So there is no need to do any extra processing at the receiver. Another interesting benefit is that you can design this artificial noise signal for your own purpose. For example, you can design it in such a way to reduce the peak to average power ratio or reduce out of band emission. Moreover, you can use this artificial extra signal for sensing purpose in joint radar communication. Now, coming to the demerits of these techniques, first of all, when you are using some, you want to generate artificial noise, you have to use some power. So there is some degradation in the performance because you are using some resources for generating artificial noise. Another thing that is needed is that you need to know the channel state information. As I explained earlier here, the transmitter should know the channel corresponding to legitimate receiver. This channel is not needed, but he must know this channel, legitimate receiver's channel. I want to mention here is that although attacker is passive and we assume that her channel is not known, this technique will work even if we don't know the channel of attacker. But if we know the attacker channel, it can further enhance the performance, in fact. But here we are assuming we don't know the channel of attacker. So from the demerits perspective, we need to know the channel of legitimate receiver, and the channel quality is very important here. If the channel quality, because from the practical point of view, there are some kind of errors in the estimation, so it can degrade the performance. Another, as I mentioned, the channel estimation error will degrade the performance of these techniques because it will cause leakage of the artificial noise to the legitimate node. Finally, if artificial noise signal is not properly designed, it may cause increase in peak to average power ratio and out of band emission. Like here, if you design it well, you can use it for a good. But if the design is, if you are not properly designing this signal, it can cause peak to average power ratio, out of band emission. Now, what is orthogonal blinding or artificial noise based technique? Let's go into the detail how we can design a null space of what is the null space of channel and how are we putting the noise in null space of channel. Now, under this, let's assume that here we have an Alice with 2 antennas and Bob and Eve have single antennas. The transmitter choose, let's assume that XR is the transmitted signal. It is made up of two things. One is our signal of interest, that is SR, and we are designing a noise signal FR, and we are sending the superposition of SR and FR, where both of SR and FR are assumed to be complex Gaussian vector, and FR is chosen to be lie in null space of channel, such that when FR passes through the channel, the result is 0. And how we are designing FR? FR is actually designed based on ZR, which is an orthonormal basis for null space. So we extract ZR, which are the orthonormal basis of the channel, and we use this orthonormal basis of channel to design FR. We multiply orthonormal basis of channel with the noise signal to design this FR, and we add it to our signal. When this signal passes through channel, it will hurt the attacker without hurting the legitimate node. For example, look here, we have a signal XR, which is the superposition of our signal and a noise signal in the null space. When it passes through legitimate receiver, as you see, as I explained earlier, at the legitimate receiver, when it passes through legitimate channel, FR and HR becomes 0, so legitimate receiver will not see anything. Where, as I explained earlier, HR FR becomes 0 because FR is ZR into VR, and ZR is the basis for the null space of channel. On the other hand, the attacker will receive the following signal, and HEFR is not 0 for him. More clearly here, if we see what's going on, we have a legitimate transmitter Alice designed based on legitimate receiver channel null space ZR, which is orthonormal basis for the null space of the channel. We are designing an artificial noise, and when it passes through the channel at the legitimate receiver, we are observing a clean signal. On the other hand, it will degrade the performance of attacker. Finally, to show the performance of artificial noise, I compare two cases. The first case is I'm using transmitter precoding based physical layer security techniques and artificial noise based security techniques. The left figure shows the bit error rate performance at Bob and eavesdropper. Here it is observed that, as you can clearly see from the blue curve, it is for transmitter precoder, where I am designing a precoder based on the channel of legitimate node. There is a gap between this black curve and blue curve when I use transmitter precoder. On the other hand, when I use artificial noise based technique, where I am using 20% of the total power for the noise generation, there is little degradation for the performance of legitimate node, but it degrades the performance of eavesdropper significantly. As you see, if you see the gap between the performance of legitimate node and attacker, it is a huge performance gap just by using 20% of total power. Similar things observed at these throughput curves. Finally, what are the challenges? As I explained earlier, we need channel set information of legitimate node. Its quality is important. Then design of signal in sparse and rich environment is also different. For example, in the rich environment, as I explained earlier, we can exploit null space of the channel. But if you go to sparse environment, you have to consider like I will explain earlier. In the sparse environment, you will see you can use beamforming towards narrow beam of signal towards legitimate node, and for the other direction, if you know the attacker, you can send noise beams towards attacker, or if you don't know the attacker, you can send isotropic noise to other directions. Other challenges, power allocation between noise signal and information is very important. Another thing is artificial noise design should also consider PAPR constraint. Another very important thing is that the channel state information between legitimate transmitter and legitimate receiver should be secure. I mean, by any way, an attacker will not able to observe this channel state information, because if he knew this channel state information, he can do reverse engineering and can remove the artificial noise. There are some works in the literature that are talking about this, that CSI Snoop and this kind of work, they are able to extract the information between the legitimate information related to legitimate nodes channel by reverse engineering the precoder matrix. Finally, there are some work that are exploiting blind signal analysis to attack these artificial noise based techniques. Now, a quick comparison between these techniques, beamforming based techniques, zero forcing, and artificial noise. Now, in beamforming based techniques, as I explained earlier, we have an Alice, legitimate receiver Bob, and eavesdropper. Now, based on the channel of legitimate node, we can try to focus our beam or towards legitimate node, or we design our signal based on the channel of legitimate node. But in beamforming, there is some leakage to the eavesdropper as well due to the side lobes. On the other hand, if we knew the channel of eavesdropper, we can design zero forcing, in which you can totally cancel or totally remove our legitimate signal from the eavesdropper, so we will not able to listen. But in this case, you need to know the channel of attacker. Finally, artificial noise based techniques, even there is some leakage, we can put some the noise generation or noise using our noise will enable us secure communication, because this noise will not hurt the legitimate node, but we can make sure that it is hurting the attacker. Now, there are other concepts similar to artificial noise. As I explained earlier, in sparse environment, you can launch main beam of transmission toward legitimate node and noise towards the attacker. Other than that, we have some things in the literature, friendly jamming based concept. In friendly jamming based concept, we are using the concept of cooperative communication for generating artificial noise or jamming signal in order to enable secure communication. For example, consider the first scenario A. We have an Alice, Bob, and Eve. We hire or an external jammer or friendly jammer that will hurt the attacker without hurting ourselves. Another case is that we have a cooperative communication with the help of relay, and the relay is a trustable relay. So there's an attacker who is trying to listen the communication from relay to Bob. We can hire a jammer technique or a jammer, friendly jammer, to hurt his communication. Finally, there are some cooperative communication technique in which we have an untrusted relay. In these cases, Alice and Bob. So in the first transmission, Alice will send a signal to relay. At the same time, Bob will send a noise signal to that untrusted relay. And in the next transmission, relay will send a signal that he is observed or she observed in the first transmission to the Bob. As Bob know what it transmitted in the first transmission, so in the second transmission from relay, it can remove that interference. Finally, there are other cooperative jamming based security technique in which group of relays can launch a artificial noise beam toward the attacker while ensuring clean signal at the legitimate node. Recently, they are also hiring UAV as a cooperative jammer. Finally, as I explained earlier, previously we discussed how multiple antenna based techniques can enable artificial noise. Like we need multiple antennas at the transmitter and to that whose number should be greater than the number of antennas at the receiver to enable these MIMO based artificial noise techniques. I want to mention artificial noise based techniques are applicable if even there is no MIMO in cooperative jamming based technique, or if we have single antenna at the transmitter. For example, in case of OFDM, we can still apply artificial noise based techniques, but the design will be different here. For example, in case of OFDM, we can still use artificial noise based techniques by using the degree of freedom provided by cyclic prefix, in which we design a signal based on the cyclic prefix in such a way that we, at the transmitter side, based on the channel of legitimate node, the signal is added on the in the time domain in such a way when it passes through the legitimate channel, it will be accumulated at the CP. On the other hand, at the attacker side, it will spread on to the whole signal. So the CP is discarded anyway. So in such a, so the design, as we explained earlier, the design principle that artificial noise is added in such a way that it will hurt the illegitimate node without hurting the legitimate node. Finally, there is another design possibility where we can design artificial noise in two transmission or through two antennas. For example, automatic repeat request based techniques in which you send your signal using the concept of retransmission. You can design your artificial noise in two transmission in such a way that when they combine at the receiver, artificial noise is cancelled at the legitimate node, while at the attacker it will hurt. These are some important references. For example, this is the first reference related to the first word. We have reference 3 and 4. We have our own a survey paper and another very nice paper. Reference 5 is related to the attack on artificial noise based techniques. Thank you so much for if you have any question, you can write on the comment section.